Hello, beautiful souls. Welcome to a quiet place where science meets stillness, where curiosity drifts softly into wonder. Tonight, I want you to imagine something with me. Imagine you're looking through your window at the moon, that pale, familiar light spilling across your floor, that ancient companion hanging in the darkness. Now, what if it wasn't there? Or what if something else hung in its place, something larger, closer, or impossibly distant? What if the light falling through your window tonight came from a moon that never existed, but could have? Some nights the world feels wider than it should. Stars breathe slower. Time folds in silence. Maybe that's just the mind listening to the gentle pull of something older than memory itself, the moon, our silent architect, shaping tides and time and the rhythm of life on Earth in ways we barely notice. But here's the beautiful, unsettling truth. We almost didn't have this moon at all. And if things had gone differently 4.5 billion years ago, you and I might be living under a completely different sky. Before we begin drifting through these possibilities together, if you find comfort in these quiet journeys through science and wonder, you might like to stay a while. You can gently tap the like button if this feels like the kind of night you want to remember. Subscribe if you'd like more stories told softly where knowledge becomes something you can rest inside. And ring the little bell not for noise, but so the next quiet night can find you again when you need it most. Now, let's drift. Tonight we'll slip quietly into worlds that never were, but could have been. We'll explore what Earth might look like with a different moon, or no moon at all. We'll watch oceans rise and fall in strange new rhythms, see skies that never darken, and nights that never end, and witness how the simplest change in the heavens could rewrite everything we know about life, time, and the stories we tell beneath the stars. You don't need to understand everything, just rest your thoughts here. Let curiosity do the listening. And perhaps by the end, you'll look at that familiar light through your window and see it differently, not as something that simply is, but as something impossibly beautifully rare. The moon hanging above us tonight is the result of violence. 4.5 billion years ago, when Earth was young and molten, still cooling from its own birth, something catastrophic happened. A Mars-sized planet, scientists call it Theia, slammed into the infant Earth at an angle at speeds we can barely comprehend. The collision was so powerful that it vaporized rock sent plumes of molten debris spiraling into space and nearly destroyed both worlds entirely. But from that destruction came creation. The debris didn't scatter into the void. Gravity held it close, pulling the fragments into orbit around Earth, where they slowly, patiently, over millions of years clumped together, cooling, solidifying, becoming round, becoming the moon. This is called the giant impact hypothesis, and it's the most widely accepted explanation for how our moon came to be. Not a gentle birth, but a violent one. Not planned, but accidental. A cosmic collision that could have ended everything instead gave us the companion that would shape life itself. And here's what makes it so remarkable. The size and distance of our moon are almost absurdly perfect. If Theia had been smaller, the debris might have scattered too thinly to form a moon at all. If the collision had been more direct, Earth might have been obliterated entirely. If the angle had been sharper, the fragments might have fallen back to Earth or drifted away into the solar system, lost forever. Instead, we got a moon just large enough to stabilize us, just far enough to allow us to breathe, just close enough to pull at our oceans and our hearts. Scientists suggest that the moon is moving away from us even now, about 3.8 centimeters every year. Slowly, almost imperceptibly, it drifts. In a few 100 million years, it will be too far away to create total solar eclipses. Those breathtaking moments when the moon slides perfectly across the face of the sun, blocking its light entirely, turning day into twilight. That perfect alignment, that cosmic coincidence will be gone. But for now, we have it. This exact moon, this exact distance. And it's easy to forget how extraordinary that is. Not all moons are born this way. Some moons form alongside their planets, condensing from the same swirling disk of gas and dust that gave birth to the worlds they orbit. Others are captured rogue asteroids or fragments from elsewhere in the solar system, pulled in by a planet's gravity and held in place unwilling prisoners turned permanent companions. Mars has two small moons, Phobos and Deimos. Tiny, irregular, more like potatoes than spheres. Scientists believe they're captured asteroids snatched from the asteroid belt and locked into orbit. They're so small, so light, that they barely affect Mars at all. No tides, no stabilization, just two silent, lonely rocks tumbling through the Martian sky. Jupiter has 79 known moons. Some are massive. Ganymede is larger than the planet Mercury. Others are barely a kilometer across fragments of ice and rock orbiting in the outer darkness. Most of them are captured objects pulled in by Jupiter's immense gravity over billions of years. They're a collection, not a family, a gallery of accidents. But Earth has one moon, just one. And it's not too big, not too small, not too close, not too far. It's just right. The moon's size relative to Earth is unusual in our solar system. Most moons are tiny compared to their planets, mere footnotes in the gravity of gas giants. But our moon is about 1/4 the diameter of Earth. That's enormous proportionally. Some astronomers even call the Earth-Moon system a double planet rather than a planet and satellite because the moon is so significant, so present, so influential. And that influence runs deeper than we often realize. The moon pulls at Earth with its gravity, not enough to tear us apart, but enough to create tides, those twice-daily risings and fallings of the ocean that have shaped coastlines, ecosystems, and evolutionary history for billions of years. It's because of the moon that we have intertidal zones, those in-between places where land and sea meet and mingle, where life learned to survive both wet and dry, both submerged and exposed. Some scientists believe that tides played a crucial role in the origin of life itself. The rhythmic washing of nutrients into shallow pools, the concentration of organic molecules. The cycling between wet and dry, these tidal dynamics may have been the crucible where the first complex chemistry began, where the first living things stirred in the ancient seas. Without the moon, there would be no tides, or at least no tides like the ones we know. The sun also creates tides, but they're much weaker, only about 40%, the strength of the moon's pull. If the moon vanished tomorrow, Earth's oceans would still rise and fall, but barely. The rhythm would be faint, almost unnoticeable. The intertidal zones would shrink. Ecosystems that depend on the ebb and flow of the sea would struggle, adapt, or disappear. But the moon's influence goes beyond water. It also stabilizes Earth's axial tilt. Right now, Earth is tilted at about 23.5 degrees relative to its orbit around the sun. That tilt is why we have season summer, when our hemisphere leans toward the sun, winter when it leans away. It's a gentle, predictable rhythm that life has adapted to for hundreds of millions of years. But without the moon's gravitational anchor, that tilt would wobble. Slowly, over tens of thousands or millions of years, Earth's axis would shift, sometimes tilting more, sometimes less, sometimes swinging wildly between extremes. Scientists call this axial precession, and on a moonless Earth, it would be far more chaotic. One era might see the poles pointed almost directly at the sun, creating extreme seasonal variations. Endless summer at one pole, endless winter at the other. Another era might see the axis flatten, reducing seasons almost entirely, turning Earth into a world of eternal spring or eternal monotony. Life would struggle to adapt. Climate would become unpredictable. Ice ages and heat waves could arrive without warning, without pattern, without the steady rhythm that allows ecosystems to prepare and survive. Mars is a cautionary tale. Mars has no large moon to stabilize it. Phobos and Deimos are too small, too light. And so, Mars wobbles. Its axial tilt has varied dramatically over millions of years, sometimes as low as 15 degrees, sometimes as high as 35 degrees or more. That instability may be one reason Mars lost its thick atmosphere and became the cold, dry desert it is today. Without a stable climate, without predictable seasons, life, if it ever existed, there had little chance to take hold and thrive. Earth, by contrast, has been stable, steady, predictable, and the moon is the reason why. But there's more. The moon also affects the length of Earth's day. When Earth first formed, it spun much faster than it does now. A day might have been only 6 to 8 hours long, but the moon's gravity has been slowing us down ever so gradually through a process called tidal friction. As the moon pulls at Earth's oceans, creating bulges of water that move across the planet's surface, those bulges create drag, a kind of gentle brake on Earth's rotation. Over billions of years, that braking effect has lengthened our days from 6 hours to 24. And it's still happening. Every century, Earth's day gets a tiny bit longer, about 1.7 milliseconds per century. It's imperceptible in a human lifetime, but over geological time, it's profound. And as Earth slows, the moon drifts away. It's a trade-off, a dance of energy and momentum. The rotational energy Earth loses is transferred to the moon, pushing it into a slightly higher orbit. 3.8 centimeters per year. Slowly, steadily, the moon is leaving us. One day, billions of years from now, the moon will be so far away that it will no longer have any significant effect on Earth's rotation. The tides will be weak. The axial tilt may start to wander. And Earth will spin alone, unanchored in a way it hasn't been since before the moon existed. But that's a distant future. A future so far away, it feels almost like myth. For now, we have this moon, this companion, this silent architect. And it's easy to take it for granted, to look up at night and see just another light in the sky, just another feature of the world we were born into. But the truth is stranger and more beautiful than that. The moon we have is not inevitable. It's not guaranteed. It's the result of a collision that could have gone 1,000 different ways. It's the product of luck and physics and time, and it has shaped every living thing on this planet in ways we're still discovering. Think about it for a moment. The rhythm of your own body, the way you sleep and wake, the way your energy rises and falls, these patterns are older than humanity. They echo the tides, the cycles of the moon, the turning of the Earth beneath the light of its companion. Some animals are even more attuned. Sea turtles time their nesting to the full moon when high tides help them reach the shore. Corals spawn in synchronized pulses timed to lunar cycles, releasing millions of eggs and sperm into the water all at once. Wolves. Despite the myths, don't actually howl more at the full moon. But many creatures do change their behavior in subtle ways, responding to light levels, tidal rhythms, and cues. We're only beginning to understand. We are moon creatures, whether we realize it or not. And so, the question becomes, what if things had been different? What if the collision 4.5 billion years ago had created something else? A moon twice as large, or half as far away, or not at all? What if Earth had captured a passing asteroid and ended up with 3 small moons instead of 1? What if the fragments from the impact had formed a ring like Saturn's instead of a sphere? Each of these possibilities would have created a different Earth, different oceans, different climates, different life, and maybe no us at all. The moon is not just a light in the sky, it's a sculptor, a timekeeper, a guardian. It has written itself into the geology of our planet, the biology of our ecosystems, the mythology of our cultures. It's in our calendars, our stories, our poems, our dreams. And tonight, as you rest here in the quiet, it's still up there, still pulling, still shaping, still drifting slowly away. But before it goes, before that distant future arrives, we have time. Time to wonder, time to explore, time to ask what if. So let's not waste it. Let's step into the possibilities one by one and see what other moons might have made of this world. Let's watch oceans rise impossibly high, skies fill with multiple crescents, and nights stretch into something we can barely imagine. Because the moon we have is extraordinary, But the moons we might have had, they would have been worlds unto themselves. What if you looked up tonight and saw nothing? No pale crescent, no glowing circle, just stars scattered across an empty, endless black. What if Earth had never had a moon at all? What if that collision 4.5 billion years ago had sent the debris spinning away into space, lost forever, leaving our planet to spin alone in the darkness? It sounds peaceful, doesn't it? A simpler sky, a quieter night. But the truth is far stranger. A moonless Earth would be a world almost unrecognizable. A world where oceans barely moved, where seasons swung wildly between extremes, where days lasted only a few hours and storms raged with unimaginable fury. It would be a world where life, if it arose at all, would have taken radically different forms, adapting to chaos instead of rhythm, to instability instead of cycles. This is not a world of peace. This is a world of relentless, beautiful violence. And tonight we're going to drift through it piece by piece and see what Earth might have become without its silent companion in the sky. Let's begin with the most obvious change, the tides. Right now, as you sit here, the ocean is rising and falling. Twice a day, every day, the water climbs up the shore and then retreats, pulled by the moon's gravity. This rhythm is so constant, so reliable, that we barely think about it. But on a moonless Earth, that rhythm would vanish. The sun would still create tides, weak ones, gentle risings of maybe 30 centimeters instead of meters. But without the moon's pull, the ocean would become almost still, stagnant in a way. The great mixing of nutrients that happens in coastal areas where tides carry food from the deep ocean into shallow zones would slow to a trickle, and that would change everything. Scientists believe that intertidal zones, those narrow strips of land between high and low tide, were critical to the evolution of complex life. These are places where organisms had to adapt to being underwater part of the time and exposed to air the rest of the time. They had to learn to survive both, and in learning that they developed lungs, limbs, and the ability to leave the ocean entirely. Without strong tides, those zones would shrink dramatically. Maybe they would disappear altogether. And if that's true, then the evolutionary pressure that pushed life onto land might never have existed. Fish might never have crawled out of the sea. Amphibians might never have evolved. And the entire history of terrestrial life, dinosaurs, mammals, birds, humans might never have happened. It's a humbling thought, isn't it? That the moon didn't just light our nights. It might have been the reason we exist at all. But let's keep going. Let's look at what else would change. Without the moon, Earth's rotation would be faster, much faster. When Earth first formed, a day was only about 6 hours long. Over billions of years, the moon's gravitational pull has been slowing us down, stretching those 6-hour days into the 24-hour days we know now. It's a process called tidal breaking, and it's still happening every century. Our days get about 1.7 milliseconds longer. But without the moon, that braking effect would be gone. Or at least it would be far weaker, driven only by the sun's much gentler pull. Scientists estimate that on a moonless Earth, a day might still be somewhere between 6 and 12 hours long. The planet would spin like a top, fast and furious, dragging the atmosphere along with it. And that would create winds unlike anything we've ever seen. Think about hurricanes. They form because of differences in temperature and pressure, but their strength is limited by the Coriolis effect, the way Earth's rotation influences the movement of air and water. On a faster spinning Earth, the Coriolis effect would be much stronger. Winds would spiral more tightly, more violently. Storms would be more frequent, more powerful, more destructive. Some climate models suggest that a fast-spinning Earth might have near-permanent superstorms in certain latitudes, massive cyclones that never fully dissipate, fed constantly by the rapid rotation and the temperature differences between equator and poles. The sky would be in constant motion. Clouds would race across the horizon. Weather patterns would shift in hours instead of days. It would be a world where stillness is rare, where calm is the exception, not the rule. And then there's the question of axial tilt. Right now, Earth is tilted at 23.5 degrees. That tilt gives us seasons, predictable cyclical changes in temperature and daylight that life has adapted to over hundreds of millions of years: spring, summer, autumn, winter. A rhythm as steady as the tides. But the moon is what keeps that tilt stable. Without the moon's gravitational anchor, Earth's axis would wobble. Not quickly, this would happen over thousands or millions of years, but dramatically. Computer simulations show that a moonless Earth's axial tilt could vary anywhere from 0 degrees to 85 degrees or more over geological time. Imagine what that means. At 0 degrees of tilt, there would be no seasons at all. The equator would always be hot, the poles always cold, and the in-between latitudes would experience an eternal, unchanging climate. Life in the tropics might thrive, but the polar regions would be locked in permanent ice and temperate zones. Places like where most humans live today would be monotonous static, without the variety that drives adaptation and evolution. But at the other extreme, 85 degrees of tilt, the poles would point almost directly at the sun during summer. One pole would bask in continuous sunlight for months, heating to tropical temperatures, while the other would freeze in months-long darkness. Then, half a year later, the situation would reverse. The equator, meanwhile, would receive almost no direct sunlight and might become the coldest place on the planet, a frozen belt encircling the globe. And the worst part, these extremes wouldn't stay constant. They would shift unpredictably over millions of years. One era might have moderate tilt and gentle seasons. The next might swing to extremes, plunging ecosystems into chaos. Life would struggle to adapt. Species that evolved during a stable period might go extinct when the tilt changed. Ice ages and heat waves would come and go, without pattern, without warning. Evolution would be a constant race against an unstable climate, and many lineages simply wouldn't make it. Mars is the clearest example of this instability. Mars has no large moon. Its two tiny satellites, Phobos and Deimos, are too small to provide any meaningful stabilization. And as a result, Mars's axial tilt has varied wildly over its history, sometimes as low as 15 degrees, sometimes as high as 60 degrees or more. Scientists believe this instability may have contributed to Mars losing its thick atmosphere. During periods of extreme tilt, the polar ice caps would have been exposed to intense sunlight, vaporizing into the atmosphere. Then, during other periods, that water vapor would freeze out again, burying itself in the regolith, beyond the reach of the thin Martian air. Over time, the atmosphere thinned, the climate destabilized further, and Mars became the cold, dry desert we see today. Earth, by contrast, has been stable, steady, thanks to the moon. But without it, we might have followed Mars's path. Or we might have developed life that was adapted to chaos, organisms that could hibernate through extreme climate shifts, species that migrated constantly in search of habitable zones, ecosystems that collapsed and reformed in cycles lasting millions of years. It's hard to say which version of Earth would have emerged, but one thing is certain, it wouldn't have been the Earth we know. Now, let's think about the night sky itself. Without the moon, the night would be darker, much darker. The moon reflects sunlight, brightening the night by a factor of about 400,000 times compared to starlight alone. On a clear night with a full moon, you can see your shadow. You can walk without a flashlight. You can read if the print is large enough. But on a moonless Earth, the only light would come from stars. And stars, as beautiful as they are faint. The night would be profoundly, utterly dark. Human eyes would adapt. Our ancestors might have evolved even better night vision than we have now. But it would still be a world where nighttime was a time of blindness, of vulnerability, of stillness. And that would change behavior. Many animals are crepuscular active during twilight, when there's just enough light to see, but predators are less active. But without the moon, twilight would be the only time of partial visibility. Midnight would be pitch black. Nocturnal animals as we know them might not exist, or they would rely entirely on other senses. Echolocation, like bats, or heat sensing like pit vipers, or bioluminescence like deep-sea creatures. Imagine forests where the only light at night comes from glowing fungi, glowing insects, glowing eyes. Imagine oceans where bioluminescent plankton create waves of ghostly blue light, the only way to see the surf in the darkness. It would be eerie, alien beautiful, in a way that's hard to describe. And then there's the cultural impact. Humans have always been shaped by the moon. Our earliest calendars were lunar, based on the cycles of the new moon, full moon, waxing and waning. The word month comes from moon. Many ancient cultures tracked time by counting moons, not suns. The moon was a clock, a calendar, a guide for planting and harvesting and hunting. But without the moon, those cycles wouldn't exist. We would have only the sun to guide us, the rising and setting, the slow progression of seasons. Time would feel different, longer perhaps, more linear, less cyclical. And our stories would be different too. No moon goddess like Selene or Diana or Chang'e. No werewolves transforming under the full moon. No poems about moonlight on water. No songs about the man in the moon. No myths about the moon being the eye of a god or the home of the dead. The moon is woven into human culture so deeply that it's hard to imagine what we would have dreamed about instead. Maybe we would have worshipped the stars more. Maybe we would have told stories about the Milky Way, that river of light flowing across the darkness. Maybe our myths would be about constellations instead of crescents, about distant suns instead of a nearby companion. Or maybe in the deep darkness of a moonless night, we would have turned inward, told stories around fires because the fire would be the only light, become creatures of the day, afraid of the night, building our entire civilization around the rhythm of sunrise and sunset. It's impossible to know, but it's clear that we would be different, not just physically, but culturally, psychologically, spiritually. The moon didn't just shape our planet, it shaped us. And yet, there's one more thing to consider. A moonless Earth might never have developed intelligent life at all. Not because intelligence requires a moon necessarily, but because intelligence requires stability. It requires ecosystems that persist long enough for complex food webs to develop, for species to evolve intricate behaviors, for brains to grow larger and more sophisticated over millions of years. But on a moonless Earth, with its chaotic climate, its fast rotation, its weak tides and unstable axis ecosystems might be too fragile. Species might go extinct too quickly. Evolution might favor simple hardy organisms, bacteria, lichens, hardy plants that can survive almost anything, but never have the time or the stability to become complex. Or maybe life would have found a way. Maybe it would have adapted to chaos-developed resilience we can't imagine, and eventually produced something intelligent but alien. A species that doesn't think in terms of cycles and rhythms because their world has none. A species that sees time as random, unpredictable, something to endure rather than measure. We can't know, but we can wonder, and in wondering, we begin to see how extraordinary our own world is. The moon we have is not just a light in the sky. It's a stabilizer, a timekeeper, a sculptor of oceans and atmospheres and evolutionary paths. It's the reason we have 24-hour days instead of 6. The reason we have stable seasons instead of chaotic swings. The reason we have tides that shaped life's journey onto land. A moonless Earth would still be Earth. It would still orbit the sun, still have water and air and the raw ingredients for life. But it would be a different Earth, a harsher one perhaps, a lonelier one certainly. And as we drift onward into other possibilities, other moons that might have been, it's worth holding on to that thought. The absence of something can be just as powerful as its presence, and sometimes the most important things are the ones we never think about until we imagine them gone. So, before we move forward, take a moment. Picture that empty sky. Feel the weight of that darkness. And then when you're ready, we'll step into the opposite extreme, a world where the moon is not absent but overwhelming. A world where the sky is dominated by something so large, so close, that it swallows the horizon and pulls the oceans into mountains of water. We'll explore what it means to live beneath a giant moon and whether beauty and terror can exist in the same light. Now imagine the opposite. Imagine looking up at the night sky and seeing something so vast, so impossibly close that it fills half the horizon. A moon so large it doesn't just hang in the darkness, it dominates it. Its craters are visible to the naked eye, deeper and sharper than mountains. Its light is so bright that shadows are crisp at midnight, that you can see colors in the darkness, that the night feels almost like a second, softer day. Beautiful, yes, but also terrifying. Because a giant moon wouldn't just change the way the sky looks. It would reshape the oceans, crack the ground beneath your feet, and pull at the planet with such force that Earth itself would groan under the strain. This is not a gentle companion. This is a force of nature, one that could create wonders, yes, but also catastrophes beyond imagining. So, let's drift into this world together. A world where the moon is 2, maybe 3 times larger than the one we know. A world where the night sky is no longer something to gaze at peacefully, but something that demands your attention, your awe, and perhaps your fear. Let's begin with size. Our moon is about 3,475 kilometers in diameter. Not small, but manageable. It sits at an average distance of 384,000 kilometers from Earth, close enough to pull at our oceans, but far enough to allow us space to breathe. But what if instead of our moon, Earth had captured something like Titan Saturn's largest moon, which is 5,150 kilometers across, or Ganymede Jupiter's giant, which is even larger at 5,268 kilometers? These aren't just bigger moons. They're worlds in their own right, larger than the planet Mercury, massive enough to have their own atmospheres and complex geology. Now imagine one of them hanging in Earth's orbit. The first thing you'd notice is the light. A moon twice the size of ours would reflect roughly 4 times as much sunlight back to Earth. That doesn't sound like much, but it would transform the night. Full moons would be blinding so bright that streetlights might seem unnecessary, that animals adapted to darkness would struggle, that entire ecosystems built around the cover of night would collapse or evolve in radically different directions. Some scientists suggest that on a planet with a giant moon, nocturnal animals might never have evolved at all. Or if they did, they would need to adapt to a world where night is never truly dark, where there's always light spilling across the landscape, where hiding is nearly impossible. Birds might sing at midnight, confused by the brightness. Plants might photosynthesize weakly even during the night. Human circadian rhythms, those internal clocks that tell us when to sleep and wake, might be thrown into chaos because our brains rely on darkness as a signal for rest. On a world with a giant moon, darkness would be rare, and sleep as we know it might become something different entirely. But light is the least of our concerns. The real danger comes from gravity. Right now, the moon pulls at Earth with enough force to create tides, those twice daily risings of the ocean that can reach several meters in some places. But the strength of tidal force depends on both the mass of the object pulling and its distance from you. A moon twice as large would have roughly 8 times the mass. And if it were at the same distance, its tidal pull would be 8 times stronger. 8 times. That means tides that don't rise by meters, but by tens of meters. Maybe hundreds depending on the coastline and the shape of the seabed. Picture this. You're standing on a beach at low tide. The water is far away, kilometers in the distance, exposing mudflats and sandbars and ancient shipwrecks that are usually submerged. And then, over the course of a few hours, the water begins to return. But it doesn't creep in slowly. It surges, it rushes, it climbs higher and higher, faster and faster, until it's not a tide, but a wall, a moving mountain of water that swallows the beach, the cliffs, the coastal cities, everything in its path. And then 6 hours later, it retreats again, pulling back, draining away, leaving behind wreckage and debris and a landscape scoured clean. This would happen twice a day, every day, without fail. Scientists call these mega tides, and they would make Earth's coastlines almost uninhabitable. No permanent structures could survive, no ports, no cities, no villages built near the sea. Humanity would be forced inland away from the oceans, living on high ground, and watching the water from a distance, waiting for the twice-daily deluge to pass. And it's not just the oceans. The moon's gravity would also pull at the solid Earth itself, a phenomenon called Earth tides. Right now, this happens, but only slightly. The ground beneath your feet rises and falls by about 30 centimeters every day, flexing under the moon's pull. You don't notice it because it's so gradual, so gentle. But with a giant moon, those flexes would be much larger. The ground would heave, mountains would shift. Tectonic plates already under constant pressure would be stressed even further by the relentless tugging of the giant moon overhead. And that means earthquakes. Lots of them. On Earth, most earthquakes happen along fault lines, places where tectonic plates grind against each other. But with a giant moon, the constant flexing of the crust would create new stresses, new fractures, new points of failure. Earthquakes would be more frequent, more widespread, and possibly more devastating. And then there are the volcanoes. One of the best examples of tidal stress in our solar system is Io, one of Jupiter's moons. Io is roughly the same size as our moon, but it orbits much closer to Jupiter, and Jupiter is enormous, with a gravitational pull that dwarfs anything Earth could produce. As a result, Io is constantly squeezed and stretched by Jupiter's gravity, generating so much internal heat that the moon is covered in active volcanoes, hundreds of them, erupting constantly. Io's surface is the most geologically active place in the entire solar system, resurfaced over and over again by rivers of lava. Now, imagine Earth in a similar situation. A giant moon wouldn't turn Earth into Io. Our planet is much larger and more massive, so the effects would be less extreme, but it would definitely increase volcanic activity. Magma chambers beneath the crust would be heated by the constant flexing. Dormant volcanoes might wake up. New vents might open. And regions that are currently stable might become active again, spewing ash and lava and gases into the atmosphere. And here's the thing, volcanic activity isn't just destructive, it's also creative. Volcanoes release gases, carbon dioxide, sulfur dioxide, water vapor that help build and maintain atmospheres. They also deliver nutrients to the soil, making volcanic regions some of the most fertile places on Earth. So, while a giant moon would make the planet more dangerous, it might also make it more dynamic, more alive, in a strange, violent way. But there's a limit to how much stress a planet can take. If the moon were too large or too close, Earth would reach a point called the Roche. Limit the distance at which tidal forces become so strong that they overcome the gravitational force holding an object together. Cross the Roche limit, and the moon wouldn't just pull at Earth. It would start to tear itself apart. Bit by bit, the moon would fragment. Its surface would crack. Chunks of rock would break away and spiral inward, some falling to Earth, as meteors, others scattering into orbit. Over time, the moon would disintegrate entirely, forming a ring around Earth, a glittering band of ice and stone, beautiful and deadly, encircling the planet like Saturn's rings. And during that process, the bombardment would be catastrophic. Meteors raining down constantly day and night for thousands or even millions of years. The sky would be filled with shooting stars, but they wouldn't be wishes, they'd be warnings. Life on Earth would struggle to survive. Forests would burn. Oceans would boil. The atmosphere might be stripped away by the impacts. It would be an extinction event on a scale that makes the death of the dinosaurs look like a minor inconvenience. But let's assume the giant moon stays intact. Let's assume it's just inside the safe zone, large enough to dominate the sky, but not so close that it destroys itself. Even then, there's another consequence we haven't talked about: eclipses. Right now, total solar eclipses are rare and brief. The moon passes in front of the sun, blocking its light completely, but only for a few minutes, and only along a narrow path across Earth's surface. It's a cosmic coincidence the moon is exactly the right size and distance to just barely cover the sun's disk, creating those stunning moments of totality where the sun's corona blazes around the edges of the moon's silhouette. But with a giant moon, eclipses would be frequent and long-lasting. Imagine the moon passing in front of the sun and staying there, not for minutes but for hours. Darkness spreading across entire continents, not just a narrow band. The temperature dropping, the wind picking up, animals going silent, confused by the sudden night in the middle of the day. And then hours later, the light returning, slowly, gradually, like a second dawn. This would happen regularly, maybe once a week, maybe more. Entire societies would organize their lives around these events, planning activities for the hours of light and hunkering down during the hours of shadow. Plants which rely on sunlight for photosynthesis would struggle. Crops might fail if an eclipse coincided with a critical growth period. Forests might adapt by evolving species that can store energy more efficiently, or that go dormant during eclipses and wake when the light returns. And humans, we might become eclipse watchers, astronomers by necessity. Our calendars would mark not just days and months, but eclipse cycles, shadow paths, and the rhythms of light and dark imposed by the giant moon overhead. It's strange to think about, isn't it? How much of what we consider normal, the length of the day, the brightness of the night, the steadiness of the ground beneath us, depends on the moon being exactly the size and distance it is. A giant moon would be spectacular, awe-inspiring, a permanent monument in the sky, a reminder that we live in a universe of forces far greater than ourselves. But it would also be humbling, because living beneath a giant moon would mean living in a state of constant awareness of the tides of the earthquakes, of the eclipses, of the sheer gravitational presence looming above. It would be a world where nature is not a backdrop, but a participant, where the sky is not something to admire from a distance, but something that reaches down and touches you, shapes you, demands your respect. Would we have thrived in such a world? Maybe. Humans are adaptable. We've survived ice ages and droughts and volcanic eruptions and asteroid impacts. We might have learned to live with the megatides, built our cities on high ground, timed our lives around the eclipses. Or maybe we wouldn't have made it. Maybe the constant upheaval, the earthquakes, the floods, the bombardments during the moon's formation would have prevented complex life from ever taking hold. Maybe Earth would be a geologically active planet, churning with energy, but empty of anything more complex than bacteria clinging to volcanic vents. We can't know for certain, but we can imagine. And in imagining, we begin to understand just how delicate the balance is. The moon we have is not too large, not too small, not too close, not too far. It pulls at us, gently shaping our world without overwhelming it. It lights our nights without blinding us. It stabilizes our axis without locking us in place. It's a Goldilocks moon, just right. And as we continue onward into stranger possibilities still, that truth becomes clearer and clearer. The universe is full of extremes, moons that crush moons, that vanish moons, that dance in chaotic orbits. But we were given something rare, something balanced, something that allowed life not just to survive, but to flourish. So, let's keep drifting. Because the next possibility is one of the strangest of all, a world not with one moon or none, but with many. A sky crowded with crescents, a gravitational tug-of-war that never ends, and a future where even the moons themselves are not safe from each other. What if you looked up and saw not one moon but three? Three crescents hanging in different parts of the sky, each moving at its own pace, each pulling at Earth in its own direction. One rising as another sets, one waxing as another wanes. A night sky that's never quite the same twice, where the dance of light and shadow is unpredictable, chaotic, and endlessly changing. It sounds beautiful, doesn't it? Like something from a dream, or a painting, or a world in a fantasy novel. But beauty when it comes to gravity is often just another word for danger. Because multiple moons don't just create a more interesting sky, They create a gravitational battlefield, a constant tug of war where Earth's oceans, crust, and atmosphere are pulled in multiple directions at once, where stability becomes impossible and where the moons themselves might not survive. This is a world of orbital chaos, a world where the night sky is a clock that never quite keeps time. And if we're going to understand what it would be like to live there, we need to start with the most fundamental question. How would multiple moons even form? The answer is complicated. Our moon formed from a single catastrophic event, the collision between Earth and Theia. But if Earth had multiple moons, they likely would have formed differently. Perhaps Earth captured several small asteroids or comets over millions of years, pulling them into orbit one by one. Perhaps the giant impact produced not one large moon, but several smaller fragments that never merged. Or perhaps Earth formed in a part of the solar system where debris was more abundant and multiple objects coalesced into orbit simultaneously. Mars gives us a real-world example of a multi-moon system, though on a much smaller scale. Mars has two moons, Phobos and Deimos. Both are tiny. Phobos is only about 22 kilometers across, and Deimos is even smaller at just 12 kilometers. They're irregularly shaped, more like potatoes than spheres, and they're so light that their gravitational pull is almost negligible. Scientists believe they're captured asteroids snatched from the nearby asteroid belt and locked into Martian orbit. But here's the interesting part. Phobos is slowly spiraling inward toward Mars. Every century, it gets about 2 meters closer. In about 50 million years, it will cross the Roche limit and either crash into Mars or be torn apart by tidal forces, forming a temporary ring around the planet. Deimos, on the other hand, is drifting away just like our own moon. So even though Mars currently has two moons, that's a temporary arrangement. Eventually, it will have one, or none, or just a ring of debris where Phobos used to be. Now imagine Earth with a similar setup but scaled up. Not two tiny moons, but 3 or 4 moons, each about the size of our own moon, or perhaps smaller, maybe 1,000 kilometers across each. Let's call them Luna Selene and Artemis, just to give them names. And let's imagine they orbit at different distances, Luna close Selene at a medium distance and Artemis far out. What would that look like? First, the sky would be crowded. Depending on where you are on Earth and what time of night it is, you might see one moon or two or all 3 at once. Each would move at a different speed. Luna, being closest, would zip across the sky, completing an orbit in just a few days. Artemis, being farthest, might take weeks or even months. And Selene would be somewhere in between. They'd pass each other, overlap, create double or triple crescents. Sometimes they could align all 3 full moons hanging in the sky at once, flooding the night with light. Other times they'd scatter each in a different phase, one waxing, one waning, one dark, creating a patchwork of brightness and shadow. It would be mesmerizing, hypnotic even, but also deeply confusing. Our ancestors used the moon to track time. A full lunar cycle, new moon to full moon, and back again, takes about 29.5 days. And that rhythm became the basis for months' calendars and the way we organize our lives. But with 3 moons each on a different cycle, that system would collapse. How would you define a month? Do you track Luna's fast orbit, Selene's medium, 1, Artemis's slow drift? Or do you wait for all 3 to align, which might only happen once every few years? Ancient civilizations would have struggled with this. Some might have chosen to track all 3 moons separately, creating overlapping calendars that required constant adjustment. Others might have ignored the moons entirely and relied only on the sun, creating a purely solar calendar. And still others might have developed complex mathematical systems to predict when the moons would align, turning astronomy into a sacred art, practiced only by priests and scholars. But the real challenge wouldn't be cultural, it would be physical. Because 3 moons means 3 sources of tidal force all pulling at Earth simultaneously. Right now, the moon and the sun both create tides, but the moon's pull is stronger. When the moon and sun align during new moons and full moons, their tidal forces combine, creating what we call spring tides, which are higher and lower than usual. When they're at right angles during quarter moons, their forces partially cancel out, creating neap tides, which are more moderate. It's a predictable system. Sailors have used it for thousands of years to navigate coastal waters, plan departures, and avoid dangerous currents. But with 3 moons, predictability goes out the window. Each moon would pull at the oceans in its own direction. Sometimes their forces would align, all 3 tugging at once, creating super spring tides that would make even a giant moon's tides look tame. Other times, they'd pull in different directions, partially canceling each other out, creating confused turbulent waters where waves clash from multiple angles and currents swirl unpredictably. Coastal regions would be nightmares to navigate. Tides might rise and fall 3, 4, 5 times a day instead of 2. The timing would shift constantly as the moons move through their orbits. And in some places, the water might not flow in and out at all. It might just slosh back and forth, chaotically like water in a bathtub being shaken from multiple sides. Marine life would adapt, but in strange ways. Animals that currently time their behavior to tidal cycles like horseshoe crabs, which lay their eggs during spring tides, or grunion fish, which spawn on beaches during the highest tides of the year, would struggle to find reliable cues. Some species might abandon tidal timing altogether and rely on other signals like water temperature or day length. Others might evolve faster reproductive cycles, breeding whenever conditions happen to be favorable instead of waiting for a specific phase of the moon. And ecosystems that depend on the predictable exposure of intertidal zones, the rocks, tide pools, and mud flats that are sometimes underwater and sometimes dry, might fragment or disappear. Because in a multi-moon world, some areas might be constantly submerged while others are constantly exposed, and the in-between zones would be too chaotic to support stable communities. But it's not just the oceans that would suffer. The solid Earth would too. Remember? Earth tides, the way the ground flexes slightly under the moon's gravitational pull. With 3 moons, that flexing would be more frequent and more complex. The crust would be squeezed and stretched from multiple directions, heating up due to friction-stressing fault lines, and triggering earthquakes in patterns that would be almost impossible to predict. Volcanic activity might increase as well, with magma chambers destabilized by the constant shifting. Entire regions might become seismically active, even if they're far from tectonic plate boundaries. And here's the truly unsettling part. The moons themselves wouldn't be stable. In a multi-moon system, the moons don't just orbit Earth, they also interact with each other. They pull on each other gravitationally, subtly altering each other's orbits every time they pass nearby. Over time, these small tugs accumulate, causing the orbits to shift, drift, and sometimes cross. This is called orbital resonance, and it can lead to one of 2 outcomes: stabilization or catastrophe. In some cases, the moons might settle into a resonant pattern, where their orbital periods are simple ratios of each other. Say, Luna completes 3 orbits for every 1 orbit of Selene, and Selene completes 2 orbits for every 1 orbit of Artemis. This kind of resonance can actually stabilize the system, locking the moons into a predictable dance that lasts for billions of years. Jupiter's moons, Io, Europa, and Ganymede, are in such a resonance. For every orbit Ganymede makes, Europa makes 2, and Io makes 4. It's a perfect rhythm maintained by their mutual gravitational influence, and it's kept the system stable for billions of years. But not all resonances are stable. Sometimes the gravitational tugs push orbits closer together instead of locking them apart. And when that happens, collisions become inevitable. Imagine Luna and Selene drifting toward each other over millions of years. At first, the changes are imperceptible, just a few kilometers per century, barely noticeable on astronomical timescales. But eventually, their orbits cross. And one night, without warning, they collide. It wouldn't be a slow, gentle merger. It would be catastrophic. two moon-sized objects slamming into each other at orbital velocities thousands of kilometers per hour. The impact would shatter both moons, sending fragments flying in all directions. Some pieces would be flung out into space, lost forever. Others would fall toward Earth, raining down as meteors, not a few shooting stars, but a continuous bombardment lasting days, weeks, maybe months. The sky would be filled with fire. The atmosphere would heat up from the constant friction of incoming debris. Forests would ignite. Oceans would boil in places where large fragments struck the water. And the survivors, if there were any, would huddle underground waiting for the storm to pass. Eventually, the debris would settle. Some fragments would fall to Earth. Others would remain in orbit, forming a temporary ring that might last thousands of years before slowly dissipating. And Earth would be left with fewer moons than it started with, maybe just one, maybe none, depending on how complete the destruction was. This isn't science fiction. It's a real possibility in any multi-moon system. And there's evidence that similar collisions have happened elsewhere in the solar system. Pluto's largest moon, Charon, is thought to have formed from a collision between Pluto and another large object, similar to the giant impact that created our moon. But Pluto also has 4 smaller moons: Styx, Nix, Kerberos, and Hydra. Scientists believe these smaller moons are fragments left over from the same collision pieces that never merged with Charon, but instead remained in orbit circling Pluto in a chaotic dance. And here's the remarkable part: Pluto's small moons tumble chaotically as they orbit. Unlike our moon, which always shows the same face to Earth, Pluto's smaller moons spin and wobble unpredictably, their rotation affected by the gravitational pull of both Pluto and Charon. It's a hint of what a multi-moon system might be like: complex, dynamic, and inherently unstable. So, would life thrive on a multi-moon Earth? Maybe. But it would be life adapted to chaos, not stability. Species that could survive rapid environmental changes. Organisms that didn't rely on predictable tides or stable seasons. Ecosystems that could collapse and rebuild over and over again, resilient in the face of constant upheaval. And humans, if we evolved in such a world, we might be very different. Perhaps more nomadic, moving constantly to stay ahead of earthquakes and tidal surges. Perhaps more fatalistic, accepting that the sky itself is a source of danger. Or perhaps more creative, developing technologies and strategies to predict and survive the unpredictable rhythms of a multi-moon world. But there's one more consequence worth considering: the beauty of it. Because despite the danger, despite the chaos, a sky with multiple moons would be breathtaking. Imagine standing on a hilltop at night, watching 3 crescents rise one after another, each casting its own set of shadows, each lighting the landscape in a slightly different hue. Imagine the rare alignments when all 3 are full and the world is bathed in a light so bright you can read by it, so surreal it feels like a dream. Ancient peoples would have worshipped those moons, built temples to track their movements, told stories about the 3 sisters or the 3 guardians or the 3 faces of the divine. Art, poetry, music, all of it would be shaped by the ever-changing sky, by the sense that the heavens themselves are alive, dynamic, and impossibly complex. And maybe that would make it worth the chaos, because in the end, the universe isn't about safety, it's about wonder. And a sky with multiple moons would be one of the most wondrous things imaginable, a reminder that the cosmos is full of possibilities, some beautiful, some dangerous, and some both at once. But even multiple moons, chaotic as they are, still orbit at a respectful distance. They pull, they tug, they dance, but they keep their distance. So, what happens when that distance disappears? What happens when a moon comes so close that it no longer just influences Earth, but overwhelms it? That's where we're headed next, into a world where the moon isn't a distant companion, but a looming presence pulling the oceans into impossible heights and dragging itself slowly but inevitably toward destruction. Imagine a moon so close you could see its surface in perfect detail, not through a telescope, but with your naked eye. Every crater, every mountain, Every ancient lava flow frozen in stone, a moon so large in the sky that it doesn't just hang above you, it looms. It fills your vision. It pulls at you physically, measurably, with a force you can almost feel in your bones. Beautiful, absolutely, but also inescapable, oppressive even, because a moon that close isn't just a companion anymore. It's a captor. An Earth locked in its gravitational embrace would become something unrecognizable, a world of impossible tides, locked rotation, and a slow, inevitable march toward destruction. This isn't a relationship between equals. This is dominance, and in the end, one of them won't survive. So, let's step into this world. A world where the moon orbits not at 384,000 kilometers, but at just 38,010 times closer than the moon we know. A world where gravity is not a gentle pull, but an overwhelming force that reshapes oceans, land, and time itself. Let's begin with what you'd see. At 10 times closer, the moon would appear 10 times larger in the sky. That means it would cover an area roughly 100 times greater than the moon we're used to. It wouldn't be a small disk you can cover with your thumb. It would be enormous, spanning about 50 degrees of the sky, roughly the width of your outstretched hand, from thumb to pinky. When it rose over the horizon, it would dominate everything. Mountains would seem small in comparison. Buildings would look insignificant. The landscape would feel dwarfed by this massive sphere, hanging just above close enough that you'd swear you could reach up and touch it. And at night, when it was full, the light would be extraordinary. Scientists estimate that a moon 10 times closer would reflect about 100 times more light than our current moon. The night would be bright, not as bright as day, but bright enough to read without a flashlight, bright enough to see colors, bright enough that shadows would be sharp and distinct even at midnight. Animals that rely on darkness would be in trouble. Nocturnal predators would lose the cover of night. Prey species adapted to hiding in shadows would be exposed, and plants which use darkness as a signal for certain processes like closing their flowers or slowing their growth might struggle to function properly. But light is the least of the problems, because at that distance the moon's gravitational pull would be devastating. Tidal force increases dramatically as distance decreases. In fact, it follows what's called an inverse cube law, meaning if you cut the distance to 1/10, the tidal force increases by a factor of 1,000. 1,000 times stronger. Right now, the moon creates tides of a few meters in most places. But with a moon 10 times closer, those tides would reach hundreds of meters, maybe even kilometers in some locations, depending on the shape of the coastline and the ocean floor. Picture this. You're standing on what used to be a beach, but the water is gone. Not just low tide gone entirely. The ocean has retreated so far that you can see the continental shelf, the underwater canyons, the deep trenches usually hidden beneath kilometers of water. And then, slowly you hear it. A distant roar, a rumble that grows louder and louder. And you turn and you see a wall of water on the horizon. Not a wave, but a rising tide so massive it looks like the ocean itself has turned vertical. It moves fast, faster than you can run, faster than most vehicles can drive. And when it arrives, it doesn't gently wash over the land, it obliterates it. Everything in its path is swept away. Cities, forests, mountains even are battered by the sheer force of billions of tons of water surging inland. And then 6 hours later, it happens again in reverse. The water drains away, pulled back by the moon's relentless gravity rushing toward the opposite side of the planet. The landscape is scoured clean. Nothing remains but mud debris and destruction. This would happen twice a day, every day, without pause. No civilization could survive on the coasts. No cities, no ports, no infrastructure. Humanity, if it existed in this world, would be forced to live in the interior, on high plateaus and mountain ranges, anywhere far enough from the ocean to escape the twice-daily deluge. And even there, life wouldn't be safe, because the moon's gravity doesn't just pull at water, it pulls at the solid Earth too. Right now, Earth tides cause the ground to rise and fall by about 30 centimeters each day. But with a moon 10 times closer, those movements would be measured in tens of meters. The entire crust of the planet would flex and heave like a living thing groaning under the strain. Fault lines would rupture constantly. Earthquakes would shake the planet multiple times per day. Not small tremors, but massive quakes, some reaching magnitudes of 8 or 9 on the Richter scale. Buildings would need to be built to withstand constant shaking, or they simply wouldn't last. And volcanoes. They'd be everywhere. The constant flexing of the crust would generate enormous amounts of heat through friction. Magma chambers would be superheated, pressurized, and destabilized. Dormant volcanoes would wake up. New vents would open. And entire regions might become active volcanic zones, spewing lava and ash into the atmosphere almost continuously. In fact, Earth might start to resemble Io Jupiter's moon, which is the most volcanically active body in the solar system. Io orbits close to Jupiter, and the giant planet's immense gravity squeezes and stretches the moon so violently that its interior is molten. Io's surface is covered in hundreds of active volcanoes erupting, constantly resurfacing the moon faster than any other process in the solar system. Earth wouldn't be quite that extreme. Our planet is much larger and more massive than Io, so the effects would be less intense, but it would still be a geologically hyperactive world. A world where the ground is never truly still, where the landscape is constantly being reshaped by earthquakes and eruptions. And then there's the issue of rotation. Right now, Earth rotates once every 24 hours, and the moon rotates once every 27 days. But the moon's rotation is locked to its orbit. It always shows the same face to Earth. This is called tidal locking, and it happens when gravitational forces slow down an object's rotation until it matches its orbital period. The moon became tidally locked to Earth billions of years ago, but Earth hasn't become locked to the moon, at least not yet. Our planet is too massive and the moon is too far away, so the process is happening very, very slowly. But with a moon 10 times closer, the locking process would speed up dramatically. The close moon's gravitational pull would create enormous tidal bulges on Earth, not just in the oceans, but in the solid crust. And those bulges would act as a brake slowing Earth's rotation through friction. Over millions of years, Earth would spin slower and slower until eventually it stopped rotating relative to the moon. At that point, one side of Earth would always face the moon, and the other side would never see it. Half the planet would live in eternal moonlight, and the other half in eternal moonless darkness. This is called mutual tidal locking, and it's already happened elsewhere in the solar system. Pluto and its moon Charon are mutually locked. Pluto always shows the same face to Charon, and Charon always shows the same face to Pluto. They orbit each other like dancers frozen mid-spin, forever facing each other, forever bound. But for Earth, tidal locking would be catastrophic. The side facing the moon would experience constant extreme tidal forces, permanent high tides, constant earthquakes, endless volcanic activity. The side facing away would be calmer, but darker, colder, cut off from the moon's light entirely. And the boundary between the two, the terminator line where the moon-facing side meets the moonless side, would be a zone of perpetual twilight, a narrow band where conditions might be slightly more stable, but still chaotic. Life, if it existed, would cluster in that twilight zone. A thin strip around the planet where temperatures were moderate, where the tidal forces were less extreme, where survival was possible. Everywhere else would be too hot, too cold, too violent, or too unstable. But here's the truly unsettling part. Even this wouldn't last forever, because a moon that close is doomed. There's a boundary in space called the Roche limit, the distance at which an object's own gravity is no longer strong enough to hold it together against the tidal forces pulling it apart. For a moon orbiting Earth, the Roche limit is roughly 18,000 kilometers. Our hypothetical close moon at 38,000 kilometers is outside the Roche limit, but not by much. And remember, the moon is slowly spiraling inward. Just as our real moon is drifting away from Earth, a close moon would be falling toward it, pulled in by the same tidal forces that are tearing the planet apart. Eventually, the moon would cross the Roche limit, and when that happened, it would begin to disintegrate, not all at once, not in a single catastrophic explosion, but gradually, over thousands or millions of years, pieces of the moon would break away. Chunks of rock pulled loose by Earth's gravity, spiraling inward, colliding with each other, fragmenting further. Some pieces would fall to Earth as meteors' constant bombardment day and night for ages. Others would remain in orbit, spreading out into a ring around the planet. And eventually, the moon would be gone, reduced to rubble, a glittering band of ice and stone encircling Earth, beautiful from a distance but deadly up close, because any object passing through the ring would be shredded by collisions with the debris. Saturn's rings are likely the remnants of a moon that came too close. Scientists believe that one of Saturn's early moons crossed the Roche limit and was torn apart, and the fragments spread out into the magnificent ring system we see today. It's beautiful, yes, but it's also a graveyard. Earth with its own rings might look stunning, from space a pale blue globe wrapped in a silver halo. But from the surface, the rings would be a constant reminder of what was lost, and life struggling to survive beneath that broken sky would know that the companion that once lit the night is gone forever. There's something deeply melancholy about that, isn't it? The idea that closeness, that intimacy, can lead to destruction. That being too near to something, even something beautiful, can tear both of you apart. But it's not just a metaphor, it's physics. It's the way the universe works. Gravity is a double-edged force. It holds things together, yes, but it can also pull them apart. And the line between stability and catastrophe is thinner than we'd like to believe. On Earth, with the moon we exist in that perfect balance, close enough to feel the pull, but far enough to remain whole. The moon shapes our tides without drowning us. It lights our nights without blinding us. It stabilizes our axis without locking us in place. But if the moon were closer, if that delicate balance tipped, we'd enter a different regime entirely. A regime of extremes, of forces too strong to resist, of a slow, grinding march toward an ending that's written in the math, inevitable and inescapable. And yet, there's a strange beauty in it too. Because even in that doomed world, even with oceans surging and earthquakes shaking and volcanoes erupting, life might still find a way. It might adapt to the chaos, evolve to survive the extremes, and create ecosystems we can barely imagine. Perhaps deep-sea creatures would thrive, adapted to the constant churning of the oceans. Perhaps volcanic vents would host entire biomes fed by the endless geothermal energy. Perhaps species would evolve rapid life cycles, reproducing quickly to stay ahead of the destruction, living fast and dying young in a world that never rests. And perhaps intelligent life, if it arose, would be different too. More fatalistic, perhaps. More focused on the present because the future is uncertain and the ground beneath your feet can't be trusted. Or perhaps more resilient, more adaptable, more creative in finding ways to survive the unsurvivable. We can't know, but we can imagine. And in imagining, we realize how much we owe to the distance between Earth and its moon. That 384,000 kilometers of empty space is not a void. It's a cushion, a buffer, a gift. It's the reason we have stable oceans, predictable tides, and a planet that doesn't tear itself apart. It's the reason we can sleep at night without worrying that the ground will split open beneath us. It's the reason the moon is a friend, not a tyrant. But what if the moon were farther away instead? What if that cushion were even larger? What if the moon drifted so far that its influence faded to almost nothing? That's the mirror image of this scenario, and it brings its own set of quiet, unsettling consequences. Because sometimes distance isn't safety. Sometimes it's abandonment. What if the moon barely mattered at all? What if instead of hanging close and bright and influential, it drifted so far away that it became little more than a distant star? A pale dot in the darkness, barely visible, barely felt, barely remembered. What if Earth's companion became so removed that its presence was more myth than reality, more memory than force? It sounds peaceful, doesn't it? Like freedom, like independence. But distance in the language of gravity is another word for loneliness. And a moon too far away isn't a liberated companion, it's an absent one, a guardian that can no longer protect, a timekeeper that can no longer keep time. An Earth spinning without that stabilizing influence would slowly, quietly drift into chaos. This is not the violence of closeness. This is the silence of abandonment. And in some ways, that silence is even more unsettling. So, let's imagine it. A moon 3 times farther away than the one we know. Not at 384,000 kilometers, but at 1.1 million kilometers. Still in orbit, still technically there, but so distant, so diminished that its effects on Earth are barely noticeable. Let's see what that world would look like and what it would cost us to live there. First, let's talk about what you'd see in the sky. At 3 times the distance, the moon would appear 3 times smaller. Right now, the moon spans about half a degree of the sky, roughly the width of your pinky finger held at arm's length. But at 1.1 million kilometers, it would shrink to less than 1/6 of a degree. A tiny disk, a faint pale circle that you might not even notice unless you were looking for it. On a cloudy night, you might miss it entirely. On a clear night, it would be there, but unremarkable, just another point of light among the stars, barely brighter, barely larger. Children growing up under such a sky might not even realize it was a moon at all. They might think it was a planet or a bright star, or just part of the celestial backdrop, and the light it cast would be almost negligible. Right now, a full moon brightens the night by a factor of about 400,000 compared to starlight alone. But light intensity decreases with the square of distance. A moon 3 times farther away would reflect 9 times less light. That's still brighter than a star, yes, but not by much. The nights would be darker, not pitch black, but close. Dark enough that human eyes would struggle to see shapes and details. Dark enough that the concept of moonlight, as we know it, would barely exist. Poets wouldn't write about walking beneath the moon. Lovers wouldn't meet in moonlit gardens. The moon would be a footnote in the sky, not a presence. And our relationship with it, cultural, emotional, spiritual, would be fundamentally different. But the real consequences wouldn't be in the sky. They'd be here on Earth. Let's start with the tides. Tidal force weakens dramatically with distance. In fact, it follows an inverse cube law. If you triple the distance, the tidal force drops to 1/27th of its original strength. That's a massive reduction. Right now, the moon creates tides of a few meters in most places, sometimes more, in narrow bays and estuaries, where the water is funneled and amplified. But with a distant moon, those tides would shrink to just a few centimeters, barely noticeable. The ocean would still rise and fall, but so gently, so subtly that you'd need instruments to measure it. The sun would become the dominant force. Solar tides, which are normally about 40% as strong as lunar tides, would now be the primary driver. But solar tides are weaker overall, so the net result would be an ocean that barely moves at all. And that would change everything. Tides aren't just about water rising and falling. They're about mixing, about circulation, about bringing nutrients from the deep ocean up to the surface and carrying surface waters down into the depths. That mixing is what keeps the ocean alive, biologically speaking. It's what allows plankton to thrive, fish to feed, and entire ecosystems to flourish. But with weak tides, that mixing would slow down. The ocean would stratify layers of water at different temperatures and salinities sitting on top of each other without much interaction. Nutrients would stay locked in the deep. Surface waters would become nutrient poor. And productivity, the amount of life the ocean can support, would drop significantly. Coastal ecosystems would be hit especially hard. Intertidal zones, those narrow strips of land between high and low tide, would shrink to almost nothing. Maybe just a few centimeters of vertical range instead of meters. And many species that depend on those zones, crabs, barnacles, sea anemones, algae, would struggle to survive. In fact, scientists believe that intertidal zones may have been critical to the evolution of complex life. These are the places where organisms had to adapt to being both underwater and exposed to air, where they developed the ability to breathe out of water, to move across land, to survive in two worlds at once. Without strong tides, those evolutionary pressures would be much weaker. And it's possible that life might never have left the ocean at all. So, a distant moon doesn't just mean quieter seas. It might mean a fundamentally different tree of life. Fewer land animals, fewer terrestrial plants. Maybe no amphibians, no reptiles, no mammals. Just an ocean-dominated world where complexity stays in the water and never ventures onto the shore. But the ocean isn't the only thing affected. Earth's rotation is too. Right now, the moon is slowly stealing rotational energy from Earth through tidal friction. As the moon pulls at Earth's tidal bulges, it creates drag, a gentle brake on our planet's spin. That's why Earth's rotation is gradually slowing down, and why our days are getting longer by about 1.7 milliseconds per century. It's a slow process, almost imperceptibly slow. But over billions of years, it's had a massive effect. When Earth first formed, a day was only 6 to 8 hours long. The moon's tidal braking stretched those days to 24 hours. And it's still working, still slowing us down, still lengthening our days bit by bit. But with a distant moon, that braking effect would be much weaker. The tidal forces would be too faint to create significant drag, and Earth's rotation would slow down much more gradually, if at all. That means Earth might still be spinning fast. Maybe not 6 hours per day, but perhaps 12 or 15 hours. And that would have profound consequences for weather climate and the way life experiences time. A faster spinning Earth would have stronger Coriolis forces, the effect that causes winds and ocean currents to curve as the planet rotates beneath them. Storms would be more intense, more tightly wound, more destructive. Weather patterns would shift more rapidly. And the entire atmospheric circulation system, the way heat is distributed from the equator to the poles, would be different. Jet streams would be faster, hurricanes would be more frequent and more powerful, and the climate would be more chaotic, less predictable, harder for life to adapt to. But even that pales in comparison to the biggest consequence of all axial instability. Right now, Earth is tilted at 23.5 degrees relative to its orbit around the sun. That tilt gives us seasons summer and winter, spring, and fall, the rhythms that life has adapted to for hundreds of millions of years. And the moon is what keeps that tilt stable. The moon acts as a gravitational anchor, holding Earth's axis in place. Without it, the axis would wobble slowly over thousands or millions of years, but dramatically. Computer models show that a moonless Earth could see its axial tilt vary anywhere from 0 to 85 degrees over geological time. But what about a distant moon? Would it still provide enough stabilization? The answer is barely, maybe. A moon 3 times farther away would still exert some stabilizing influence, but it would be much weaker. Earth's axial tilt would still wander, though perhaps not as wildly as it would without a moon at all. Scientists estimate that the tilt might vary by 10 or 20 degrees over millions of years, not catastrophic, but enough to cause significant climate shifts. Imagine living on a planet where over the course of a few million years, the tilt gradually increases. Summers get hotter, winters get colder, the polar ice caps expand and contract, and ecosystems that evolved during one climate regime suddenly find themselves in a completely different one. Some species would adapt, others would go extinct, and evolution would be a constant race against a changing environment with no guarantee that any lineage would make it through. Mars again is our cautionary tale. Mars has 2 moons, Phobos and Deimos, but they're tiny, too small to provide any meaningful stabilization. As a result, Mars's axial tilt has varied wildly over its history. Sometimes it's been as low as 15 degrees, sometimes as high as 60 degrees or more, and that instability has had devastating consequences. During periods of high tilt, The polar ice caps melted, releasing water vapor into the atmosphere. During periods of low tilt, that water froze out again, burying itself in the regolith. Over time, Mars lost its thick atmosphere, its liquid water, and any chance it might have had for complex life. Earth with a distant moon might follow a similar path, not as extreme perhaps, but still unstable, still vulnerable, still at risk of losing the climate stability that makes long-term evolution possible. And then there's the question of eclipses. Right now, total solar eclipses are one of the most spectacular phenomena in nature. The moon passes in front of the sun, blocking it completely, revealing the sun's corona, that halo of plasma that's normally invisible because the sun's surface is so bright. It's a cosmic coincidence the moon is exactly the right size and distance to just barely cover the sun's disk. But with a distant moon, that coincidence would be lost. At 3 times the distance, the moon would appear 3 times smaller. And the sun's disk, which is about half a degree across, would no longer be covered completely. Instead of a total eclipse, we'd only ever see annular eclipses, where the moon passes in front of the sun, but doesn't quite cover it, leaving a ring of sunlight visible around the edges. It's still beautiful in its way, but it's not the same. The sky doesn't darken completely. The stars don't come out. The temperature doesn't drop. And the eerie, otherworldly feeling of totality, that sense of standing in the moon's shadow, of witnessing something rare and profound, would never happen. Ancient peoples wouldn't have feared eclipses as omens. They might have barely noticed them at all. And one of the great spectacles of the natural world would be missing from human experience. There's something quietly tragic about that, isn't there? The idea that beauty can be lost not through destruction, but through distance. That something can still exist, still be there technically, but be so far away that it no longer matters. And maybe that's the deeper truth of a distant moon. It's not that Earth would be destroyed. It's not that life would be impossible. It's that something essential would be missing. Some sense of connection, of presence, of being watched over by a companion in the sky. Cultures around the world have personified the moon. Given it names, genders, personalities, told stories about it, worshipped it, built calendars around it, used it to navigate, to measure time, to mark the passage of seasons. But with a distant moon, that relationship would be so much weaker. The moon would be a curiosity, not a presence, an astronomical object, not a cultural icon. And our myths, our poetry, our sense of connection to the cosmos would be shaped by its absence rather than its light. Perhaps we would turn to other celestial objects instead. The stars, maybe, the planets, the Milky Way stretching across the night sky. Perhaps our stories would be about constellations rather than crescents, about distant suns rather than a nearby companion. Or perhaps we would become more inward focused, less interested in the sky because the sky doesn't offer much to see, more focused on the Earth itself, on the forests and oceans and mountains, on the immediate world around us rather than the distant cosmos. It's impossible to know, but it's clear that we would be different. Not just physically, though. The weaker tides and unstable climate would certainly shape evolution, but psychologically, culturally, spiritually. The moon is not just a rock in the sky. It's a mirror, a symbol, a reminder that we're part of something larger, something ancient, something beyond our control. And when that reminder fades, when the moon becomes too distant to influence us, too faint to inspire us, we lose something essential. Not survival necessarily, but meaning, connection, a sense of place in the universe. And perhaps that's the subtlest loss of all, because it's not dramatic, it's not catastrophic, it's just quiet, a slow fading, a gradual forgetting. Until one day, looking up at the night sky, we realize that the moon we once knew is no longer there, not gone, but so far away it might as well be. But the moon has shaped more than just our oceans and our climate. It has shaped us, our stories, our calendars, our sense of time itself. And that's where the real magic lies. Because even if the moon were distant, even if it barely influenced our tides or our rotation, it would still be there in our imagination, in our culture, in the way we understand ourselves. So let's turn our attention there to the human side of the moon and see how deeply this ancient companion has written itself into our souls. The moon has never just been a rock in the sky. It's been a god, a timekeeper, a symbol of change of cycles of the eternal return. It's been painted, worshipped, measured, and sung about in every language humans have ever spoken. It's in our calendars, our myths, our poems, our prayers. And if Earth had a different moon, or no moon at all, we wouldn't just have different tides or different seasons. We would have different souls, because the moon doesn't just shape oceans and atmospheres, it shapes stories, and stories in the end shape us. So, let's drift away from the physics for a moment and into something softer, something harder to measure, but just as real. Let's explore how the moon has written itself into human consciousness and what we might have become if the companion above us had been something else entirely. This is about culture meaning and the quiet ways that celestial objects become woven into the fabric of who we are. Let's begin with time itself. The word month comes from moon. That's not a coincidence. It's a memory embedded in language, a reminder that before we had clocks, before we had calendars printed on paper, before we had smartphones to tell us the date, we had the moon. And the moon was perfect for tracking time. It moves through predictable phases, new moon to crescent to half to full and back again, completing the cycle in about 29.5 days. That's short enough to be noticeable within a human lifetime, but long enough to be useful for organizing activities, planting crops, hunting migrations, tribal gatherings, religious festivals. Nearly every ancient culture developed lunar calendars. The Babylonians tracked the moon meticulously, using it to predict eclipses and mark the passage of years. The ancient Egyptians combined lunar and solar cycles into a calendar that helped them predict the flooding of the Nile. The Islamic calendar is still lunar, with months beginning at the first sighting of the new crescent moon. The Hebrew calendar is lunisolar, balancing moon phases with the solar year. Even the Christian calendar, which is primarily solar, retains lunar influences. Easter, for instance, is calculated based on the first Sunday after the first full moon, following the spring equinox. The moon gave us structure, rhythm, a way to organize chaos into patterns. But without the moon, or with a moon too distant to be noticed, would we have developed the concept of a month at all? Maybe not. Maybe we would have relied entirely on the sun dividing the year into equal segments based on the solstices and equinoxes. Maybe our calendar would have been simpler, more geometric, less tied to observation and more tied to mathematics. Or maybe it would have been harder because the solar year is long and tracking it requires careful attention to the sun's position on the horizon over many, many days. The moon, by contrast, is obvious. It changes nightly. It demands attention. And so, the moon became not just a timekeeper, but a teacher. It taught us to observe, to measure, to anticipate. It turned us into astronomers long before we had telescopes or theories, simply by being there, cycling through its phases, marking time in the sky. But the moon gave us more than just calendars. It gave us gods. In nearly every mythology, the moon is personified, given a name. Given a gender, sometimes male, sometimes female, sometimes both, or neither. Given stories that explain its phases, its movements, its relationship with the sun and the stars. In ancient Greece, the moon was Selene, a titaness who drove a silver chariot across the night sky. In Rome, she became Luna, quiet and watchful, often depicted with a crescent on her forehead. In Egypt, the moon was Thoth, the god of wisdom, writing and magic, a male deity who measured time and recorded the deeds of the dead. In Norse mythology, the moon was Mani, a young man pursued endlessly by a wolf named Hati, who would one day catch and devour him during Ragnarok. In Japanese Shinto belief, the moon is Tsukuyomi, a god born from the right eye of the creator, deity Izanagi, representing the night and the calm mysteries hidden in darkness. The stories are different, but the reverence is the same. The moon is not just an object, it's a presence, a character in the great cosmic story. And here's what's fascinating. Many of these myths try to explain the moon's phases, the waxing and waning, the way it seems to die and be reborn every month. The ancient Mesopotamians believed that the moon god Sin was attacked by demons during the new moon, causing him to disappear, only to recover and grow strong again as the month progressed. Some indigenous cultures in North America saw the moon as a being who died each month and was resurrected, a symbol of renewal and the cyclical nature of life. In Hindu mythology, the moon god Chandra was cursed to wax and wane as punishment for neglecting his wives, the 27 lunar mansions. These aren't just stories, they're attempts to make sense of the world, to give meaning to something beautiful and mysterious. And without the moon, those stories wouldn't exist. Our mythology would be poorer, less connected to the rhythms of the natural world. If Earth had multiple moons, each waxing and waning on different cycles, our myths would be richer, but also more complex. Maybe we would have had a pantheon of moon gods, each representing a different lunar companion. Maybe they would have been siblings or rivals or lovers caught in an eternal dance. And maybe our calendars would have been impossibly complicated, trying to track 3 overlapping cycles at once. Or maybe we would have given up on the moon entirely and worshiped the stars instead. Maybe our gods would have been constellations and our stories would have been about the slow turning of the heavens, rather than the rapid phases of nearby companions. It's impossible to know, but it's clear that the moon we have shaped the stories we tell, and those stories shape the way we see ourselves. The moon is also deeply connected to human biology and behavior, or at least we believe it is. The word lunacy comes from lunar, based on the ancient belief that the full moon could drive people mad. Werewolves transform under the full moon. Women's menstrual cycles are sometimes said to align with lunar phases. And while modern science has found little evidence for this, the idea persists because the average menstrual cycle is close to 29 days, the same as a lunar month. Hospitals and police departments often report more unusual activity during full moons, though statistical studies have repeatedly failed to find any real correlation. It's a myth, yes, but it's a persistent one, embedded so deeply in culture that even people who know better sometimes feel it. Why do we believe the moon affects us? Maybe because it clearly affects the ocean, and we are after all mostly water. Maybe because the full moon is bright and brightness can disrupt sleep, making people more irritable or erratic. Or maybe because the moon is the most obvious celestial object that changes, and humans have always looked for patterns, for connections, for explanations. Without the moon, those beliefs wouldn't exist. No werewolves, no lunacy, no sense that the sky itself can reach down and touch the mind. And that would change horror stories, folklore, and the way we think about madness and transformation. But the moon's influence goes even deeper than myth and superstition. It's in the biology of the natural world. Many species have evolved to time their behavior around lunar cycles. Sea turtles, for instance, nest during full moons when high tides help them reach the shore. Corals in the Great Barrier Reef spawn in synchronized pulses, releasing eggs and sperm all at once during specific lunar phases, creating underwater snowstorms of reproduction. Certain species of worms, fish and crustaceans also time their mating to the moon, using its light as a signal. Why? Because the moon is reliable. It's been cycling through the same phases for billions of years. Evolution loves reliability. If a cue is constant, predictable, and impossible to fake, it becomes a trigger for biological events. But without the moon, or with a moon too faint to notice, those species would need different cues. Maybe they'd rely on water temperature or day length or the position of the sun. And their reproductive strategies would be different, less synchronized, perhaps more spread out over time. And that would ripple through ecosystems. Predators that time their hunts to coincide with coral spawning events would need new strategies. Fishermen who rely on lunar cycles to predict where fish will gather would be lost. and entire traditions. Indigenous knowledge passed down over generations about when to fish, when to plant, when to harvest would be built around different patterns, or maybe wouldn't exist at all. The moon is woven into the fabric of life on Earth. Not just human life, but all life. And if the moon were different, that fabric would be different too. Now, think about navigation. Before GPS, before compasses, before maps. How did sailors find their way across the open ocean? They used the stars, yes. But they also used the moon. The angle of the moon above the horizon, its phase, its position, relative to certain constellations. All of these could help determine latitude, time of night, and even direction. Polynesian navigators, some of the most skilled sailors in human history, used the moon to guide their voyages across thousands of miles of open ocean. They memorized lunar cycles, tracked the moon's path through the sky, and used its light to read the surface of the water, seeing waves' currents and the reflections of distant islands. Without the moon, ocean navigation would have been harder, maybe impossible. And the great age of exploration, the voyages that connected continents, spread cultures, and reshaped human history, might have happened differently or not at all. Even the Apollo missions, humanity's greatest journey away from Earth, were named after a moon god. Apollo, the Greek god of light and prophecy, became the symbol of our first steps into space. We didn't go to the moon just to plant a flag or collect rocks. We went because the moon called to us. Because it was there hanging in the sky, close enough to seem reachable, distant enough to be a challenge. If the moon were farther away, smaller, less prominent, would we have been as inspired to visit it? Would the space race have unfolded the same way? Or would we have turned our attention to Mars instead, skipping the moon entirely and aiming for something more difficult, more distant, more ambitious? It's hard to say. But the moon's presence, its size, its brightness, its nearness, made it an obvious first step, a symbolic goal, a place where humanity could prove it was capable of leaving the cradle and reaching for the stars. And there's something poetic about that, isn't there? The moon, which has shaped our tides and our myths, also shaped our future. It pulled us upward just as it pulls the oceans. And when we finally set foot on its surface on July 20th, 1969, it wasn't just a scientific achievement. It was a cultural one. A moment when humanity looked at the thing that had inspired so many stories, so much wonder, and said, "We can touch you now. We can stand where you stand. We can hold your dust in our hands." That moment wouldn't have been possible without the specific moon we have. A moon that's close enough to reach, bright enough to inspire, ancient enough to have been with us since the beginning. So, what would we lose if the moon were different? If it were too far away, we'd lose the myths, the calendars, the navigational guides. We'd lose the sense of connection between the sky and the earth, the feeling that the cosmos is watching us, cycling with us, moving in rhythms we can understand. If we had multiple moons, we'd have more complexity, more stories, more gods, but also more confusion, more chaos, less sense of a single guiding rhythm. If we had no moon at all, we'd be untethered, unmoored, floating in a darkness without cycles, without phases, without the quiet reassurance that something above us is marking time, keeping watch, reminding us that change is natural and renewal is always coming. The moon is not just a physical object. It's a cultural anchor, a source of meaning, a bridge between the human world and the cosmos. And as we drift toward the end of this journey, as we prepare to step back and look at the moon we actually have with fresh eyes, it's worth remembering that. Because science can tell us what the moon does, how it shapes, tides, stabilizes, axes, reflects light. But only stories can tell us what the moon means. And meaning in the end is what makes us human. So, let's bring it all together, now. Let's return to the moon. We know the moon that hangs above us tonight and ask the final question. Why this moon? Why this distance, this size, this companion? And what does it mean that we were given something so rare, so balanced, so perfectly, improbably suited to the world we call home? Here's the thing about coincidences. Sometimes they're not coincidences at all. Sometimes they're clues. whispers from the universe suggesting that something improbable, something almost impossibly rare has happened. And when you look at the moon, our moon, the one hanging above us right now, you start to realize that what we have isn't just unusual, it's extraordinary. It's a cosmic jackpot that we won without even buying a ticket. Because the moon we have is perfect. Not in a poetic sense, though it is that too, but perfect in a measurable, scientific, undeniable way. Perfect in its size, its distance, its influence. Perfect in the balance it creates between stability and change, between presence and restraint. And when you understand just how rare that perfection is, just how many things had to go exactly right for us to have this moon, and not some other version, you begin to see the world differently. You begin to see how fragile the whole thing is, how unlikely, how precious. So, let's take a moment to appreciate what we have. Let's look at the moon not as something ordinary, but as something miraculous. Because once you see it that way, you can never unsee it. Let's start with the most obvious miracle: total solar eclipses. Right now, the moon and the sun appear almost exactly the same size in our sky. The sun is about 400 times larger than the moon, but it's also about 400 times farther away. That ratio means that when the moon passes in front of the sun, it covers the solar disk almost perfectly, just enough to block the sun's surface, but not so much that it hides the corona, that glowing halo of plasma that surrounds the sun. This is stunningly rare. In our entire solar system, Earth is the only place where this happens. Jupiter's moons sometimes pass in front of the sun, but Jupiter is so far away that the sun appears tiny and the eclipses are barely noticeable. Mars's moons are too small to cover the sun at all. They just create small shadows, like watching a bird fly across the sun's face. And the gas giants don't have solid surfaces to stand on, so even if their moons created perfect eclipses, no one would be there to see them. But on Earth, we get this. We get moments when the sky darkens in the middle of the day, when stars become visible at noon, when the temperature drops and birds fall silent and the world holds its breath. We get to see the sun's corona, that outer atmosphere that's normally invisible because the sun's surface is so bright. We get to stand in the moon's shadow and feel physically the geometry of the solar system aligning around us. It's one of the most profound experiences a human can have, and it only works because the moon is exactly the size and distance it is. But here's the bittersweet part. This won't last forever. The moon is drifting away from us, about 3.8 centimeters per year. It's been doing this for billions of years, and it will continue for billions more. And as it moves farther away, it will appear smaller in the sky. In about 600 million years, the moon will be too far away to completely cover the sun. Total solar eclipses will no longer be possible. We'll still have annular eclipses where the moon passes in front of the sun, but leaves a ring of light around the edges. But that eerie, complete darkness, that perfect alignment will be gone. And here's the truly remarkable thing we're living in, the narrow window of time when this is possible. Earth is about 4.5 billion years old. The moon will continue to drift for billions of years into the future. But the window, when the moon is exactly the right size to create perfect total eclipses, that's only a few billion years, a fraction of Earth's total lifespan, and we're here, right now, in the middle of that window. Is that luck, or is it something else? Some scientists suggest that the timing isn't entirely random. Complex life, the kind that can look up at the sky and appreciate an eclipse, took billions of years to evolve. And it only evolved during the period when the moon was the right size to create stable tides, stable climate, and a stable environment. So maybe it's not surprising that intelligent life arose during the same period when total eclipses are possible. Maybe the two are connected not causally, but coincidentally, because both require the moon to be at just the right distance. It's a humbling thought, that we exist at a moment in cosmic history when the sky can do something beautiful and rare, and that in the distant future after we're gone, the sky will be different, less spectacular, less aligned. But for now, we have this, and it's worth treasuring. Now let's talk about the moon's size relative to Earth. Most moons in the solar system are tiny compared to their planets. Jupiter has 79 known moons, but even Ganymede, the largest, is only about 2% of Jupiter's mass. Saturn's moon Titan is similarly small compared to Saturn. Mars's moons, Phobos and Deimos, are barely more than captured asteroids, insignificant specks orbiting a much larger world. But Earth's moon. It's about 1.2% of Earth's mass. That might not sound like much, but it's huge compared to other planet-moon ratios. In fact, the Earth-Moon system is sometimes called a double planet, because the moon is so large and so influential that the two bodies orbit around a common center of mass, a point that's actually inside Earth, but not at Earth's center. This size ratio is critical. If the moon were much smaller, it wouldn't have enough gravitational pull to stabilize Earth's axial tilt. The axis would wander, seasons would become chaotic, and life would struggle to adapt to the constantly shifting climate. If the moon were much larger, its gravitational pull would be overwhelming, tides would be catastrophic, earthquakes would be constant, and Earth's crust might be stressed to the point of breaking, with volcanoes erupting continuously, and the surface constantly reshaped by tectonic violence. But at the size it is, the moon provides just enough stabilization without causing too much disruption. It's the Goldilocks zone of moon sizes, not too big, not too small, but just right. And then there's the distance. The moon orbits at an average distance of 384,000 kilometers. That's far enough that tidal forces are manageable, but close enough that the moon still has significant influence. It's far enough that the moon won't be torn apart by tidal stress, but close enough that it can still stabilize Earth's rotation and create the tides that shape the evolution of life. If the moon were closer, we'd have the problems we explored earlier: megatides, constant earthquakes, and eventual disintegration as the moon crossed the Roche limit. If it were farther, we'd lose the stabilization, the tides would weaken, and Earth's climate would become unpredictable. But at 384,000 kilometers, the moon sits in a perfect balance, a balance that has lasted for billions of years and will last for billions more. How did we get so lucky? The answer lies in the giant impact hypothesis, that ancient collision between Earth and Theia that created the moon in the first place. The collision had to be just right. If Theia had been too small, the debris wouldn't have been massive enough to form a large moon. If Theia had been too large, the collision might have destroyed Earth entirely. If the angle of impact had been too direct, Earth would have been obliterated. If it had been too glancing, the debris would have scattered into space instead of staying in orbit. But the collision was perfect. The debris stayed in orbit, coalesced into a sphere, and settled at just the right distance to provide stability without causing destruction. It's a 1 in a million event, maybe 1 in a billion. And it happened to us. And here's the deeper question: how many other planets in the universe have moons like ours? We don't know yet. We've discovered thousands of exoplanets, planets orbiting other stars, but detecting moons around those planets is incredibly difficult. Moons are small, faint, and hard to spot, even with our best telescopes. So far, we've only found a handful of possible exomoon candidates, and none of them have been confirmed. But based on what we know about planet formation, large moons like ours are probably rare. Most moons form either alongside their planets, in which case they're usually small, or they're captured objects, which are also typically small. Giant impacts, like the one that created our moon, require very specific conditions. A planet in the right stage of formation, an impactor of the right size traveling at the right speed, hitting at the right angle. It's possible that Earth is one of the only planets in the galaxy with a moon like this. Or maybe there are a few others scattered across billions of star systems, each one a rare gem in the cosmic ocean. Either way, we're lucky, profoundly, impossibly lucky. But luck isn't the only factor. There's also time. The moon has been shaping Earth for 4.5 billion years. That's enough time for tides to carve coastlines, for ecosystems to evolve around tidal rhythms, for Earth's rotation to slow from 6 hours to 24, for life to crawl out of the ocean and onto land. Without that time, without billions of years of gentle, consistent influence, Earth would be a different place. Maybe life would have arisen anyway, but it would have taken a different path. Maybe intelligence would have evolved, but in a different form, under different pressures, with a different relationship to the sky. The moon didn't just give us tides and stability. It gave us time for complexity to develop, time for ecosystems to mature, time for evolution to experiment, fail, adapt, and eventually produce beings capable of looking up at the moon and wondering where it came from. And now, here we are, the products of that long, slow process. Standing on a planet shaped by its moon, looking up at the sky and asking, what if things had been different? And the answer after everything we've explored is this: if things had been different, we wouldn't be here. Not as we are now anyway. Maybe not at all. A moonless Earth would be a world of chaos, fast rotation, unstable climate, weak tides, and no clear path for life to leave the ocean. A giant moon would create a world of violence, megatides, constant earthquakes, and eventual destruction as the moon tore itself apart. Multiple moons would create a world of unpredictability, chaotic tides, colliding satellites, and no stable rhythm for life to adapt to. A close moon would create a world of extremes, tidal locking, crushing gravity, and a slow spiral toward annihilation. A distant moon would create a world of loneliness, weak tides, wandering axis, and no stabilizing presence to anchor us. But the moon we have, it creates a world of balance, a world where life can thrive, a world where oceans rise and fall in predictable rhythms, where seasons come and go in stable cycles, where the night sky offers both beauty and guidance. It's not perfect. Nothing in the universe is, but it's close. Closer than we have any right to expect. And maybe that's the real lesson here. Not that we're special necessarily, not that we were chosen or destined or placed here by some cosmic hand, but that we're here in this moment, on this planet, under this moon, and that's rare enough to be worth noticing, worth appreciating, worth protecting, because the universe is full of planets, billions of them, trillions maybe, and most of them are nothing like Earth. Most of them have no moons or the wrong moons or moons that are too close or too far or too chaotic to support the kind of stable, thriving biosphere that we call home. But we got lucky. We got the right moon. The moon we needed even if we didn't know we needed it. And that moon has been with us, shaping us, guiding us for as long as there's been an us to guide. So maybe it's time to stop taking it for granted, to stop seeing it as just another feature of the night sky, just another object to glance at and move on from. Because the moon is not just an object. It's a companion, a guardian, a silent architect that has been building the world we live in, one tide at a time, one rotation at a time, for billions of years. And as we prepare to close this journey, as we drift toward the final, quiet moments of reflection, it's worth holding on to that thought. Because the moon we have is the moon we keep. And in keeping it, in appreciating it, in understanding it, we keep a little piece of the universe close to our hearts, reminding us that we are part of something vast, something ancient, something beautiful beyond words. So, here we are at the end of our journey through worlds that never were. We've drifted through darkness and light, through chaos and balance, through moons that crush and moons that abandon. We have watched oceans rise impossibly high, skies fill with multiple crescents, and nights stretch into something we can barely recognize. We've explored what Earth might have become if that ancient collision 4.5 billion years ago had gone differently, if the debris had scattered or merged into something larger, or never formed a moon at all. And now, after all of that imagining, after all those alternate realities, we return here, to this Earth, to this moon. To the pale light spilling through your window right now, the same light that's been falling on this planet for longer than anything alive can remember. And perhaps you see it differently now. Perhaps when you look up tonight, you won't just see a familiar circle in the darkness. You'll see a survivor, A companion that could have been lost, or too close, or too far, or never existed at all. You'll see something rare not just in our solar system, but possibly in the entire galaxy. Something that took an impossibly precise collision, billions of years of slow gravitational dance, and an unbroken chain of cosmic coincidences to create. The moon we have is not guaranteed. It's not inevitable. It's a gift we didn't ask for and don't always appreciate, but it's here, and so are we. Let's talk about what that means. When the Apollo 11 astronauts landed on the moon on July 20th, 1969, they weren't just visiting another world. They were visiting the object that had shaped their own, the thing that had pulled at Earth's oceans for 4 billion years, creating the tides that carved coastlines and drove evolution. The thing that had stabilized Earth's rotation, giving us seasons and climate patterns that allowed complex life to flourish. The thing that had lit humanity's nights, inspired our myths, guided our navigation, and structured our sense of time. Neil Armstrong's first words from the lunar surface were carefully scripted, iconic, immortal. That's one small step for man, one giant leap for mankind. But there's another moment, less famous, but just as profound, that captures something deeper. As Armstrong and Buzz Aldrin stood on the moon's surface, they looked back at Earth. A small blue sphere hanging in the black void, half in shadow, swirled with white clouds. Fragile, alone, beautiful beyond words. Aldrin later described the experience as magnificent desolation. The moon's surface was stark, airless, unchanging. But Earth was alive, vibrant. Everything that mattered was there, on that distant blue dot, while they stood in gray dust under a black sky. And here's what's remarkable: that perspective was only possible because the moon existed, because it was close enough to reach, because it invited us to come to visit, to stand on its surface and look back at home. The moon didn't just shape Earth, it shaped our future. It was the stepping stone that taught us we could leave our world and return safely. It was the proving ground for technologies that would later take us farther into the solar system. It was the goal that united nations, inspired generations, and showed humanity what we are capable of when we reach for something beyond ourselves. If the moon had been different, too far to reach, too dangerous to visit, or absent entirely, our relationship with space would be different too. Maybe we would have gone straight to Mars. Maybe we would have given up on human spaceflight altogether, content to send robots while we stayed home. Or maybe we would have dreamed smaller dreams, looking inward instead of upward, never realizing that the sky was something we could touch. But because of the moon, our moon, the one we have, we learned to dream bigger, to aim higher, to see ourselves not as creatures bound to a single world, but as beings capable of walking on other worlds, of reaching across the void and making the impossible real. And that legacy continues. Right now, as you listen to this, there are plans to return to the moon. NASA's Artemis program aims to land humans on the lunar surface again within the next few years, this time establishing a permanent presence, a lunar base, a gateway to deeper space, a place where humans can live and work, not for days, but for months or years. Other nations are planning their own lunar missions. China has already landed robotic rovers on the far side of the moon, the side we never see from Earth, the side that's always turned away. India. Japan and private companies are developing their own lunar landers, rovers, and habitats. The moon is no longer just a destination. It's becoming a neighborhood, a place we'll visit regularly, explore thoroughly, and eventually call a second home. And all of this is possible because the moon is exactly where it is. Not too close, not too far, not too large, not too small, just right. It's easy to forget how extraordinary that is. How many things had to go perfectly for us to have this moon, this Earth, this moment. But maybe forgetting is natural. Maybe it's human nature to take miracles for granted once they become familiar, to see the moon every night and stop noticing it. To assume that the tides will always rise and fall, that the seasons will always cycle, that the night will always be lit by that pale, steady glow. But now you know better. You know that a moonless Earth would spin faster, wobble chaotically, and offer no stable rhythm for life to adapt to. You know that a giant moon would drown coastlines twice a day and tear itself apart over millions of years. You know that multiple moons would create gravitational chaos, with tides pulling in different directions, and satellites eventually colliding in fiery destruction. You know that a close moon would lock Earth's rotation, creating a world of extremes where half the planet bakes in eternal moonlight and the other half freezes in endless darkness. You know that a distant moon would fade into irrelevance, its influence so weak that Earth's axis would drift, its tides would vanish, and its nights would be darker and lonelier. But the moon we have, it does none of those things. It simply exists quietly, steadily pulling at us, just enough to keep us stable, lighting our nights, just enough to guide us cycling through its phases, just often enough to mark time without overwhelming it. It's the perfect companion, not because it never changes, but because it changes in ways we can predict, understand, and adapt to. And perhaps that's the deepest lesson of all. Stability isn't about stasis. It's not about things staying exactly the same forever. The moon is drifting away. Earth's rotation is slowing. The tides are changing imperceptibly over millions of years. Nothing is permanent. Nothing lasts forever. But within that slow change, there's rhythm. There's predictability. There's enough consistency for life to take root, grow, adapt, and thrive. And that balance between change and stability, between movement and constancy, is what makes life possible. The moon teaches us that. It teaches us that you can be in motion and still be a foundation, that you can drift away and still be essential, that you can change slowly over eons and still be the same companion you've always been. And maybe we can learn from that. Maybe we can learn to appreciate the things that are always there, even as they change. The people who stay with us even as we all grow older. The places that shape us even as they're reshaped by time. The rhythms that guide us even as they shift and evolve. The moon has been humanity's companion for as long as there's been a humanity. It's been in our myths, our calendars, our navigation, our poetry. It's been the subject of wonder and worship science and superstition. And now, after all these centuries of looking up at it, we've finally walked on its surface, held its dust in our hands, and understood at least a little what it is and where it came from. But understanding doesn't diminish wonder. If anything, it deepens it. Because now we know that the moon isn't just a rock. It's the reason we have stable seasons. The reason we have 24-hour days. The reason life was able to leave the ocean and spread across the land. The reason we have tides and calendars and total solar eclipses. The reason we were inspired to reach for the stars in the first place. The moon is not just up there, it's in here, in our history, in our biology, in our culture, in the way we measure time, tell stories, and dream about the future. And tonight when you look up and see it hanging in the darkness, you'll know that it's not just beautiful, it's necessary, it's rare. It's the companion we almost didn't have, the guardian we never knew we needed, the silent architect that's been shaping our world since before there was anyone here to notice. So, take a moment, just a moment, and look. See the craters, the Maria, the bright highlands. See the phases waxing waning, full new cycling through their eternal rhythm. See the light it casts, the shadows it creates, the quiet presence it offers in the darkness. And maybe just for tonight feel grateful. Not in a grand dramatic way, but in the quiet, simple way, you feel grateful for something that's always been there, something you've always taken for granted, something you suddenly realize you couldn't live without. Because the moon we have is the moon we needed. The moon that made us possible. The moon that will still be there long after we're gone, pulling at oceans and lighting nights for whatever comes next. And for now, it's ours, our companion, our timekeeper, our guide through the darkness. Sleep well beneath its light. Dream gently knowing that the sky is exactly as it should be. And rest in the quiet knowledge that some things rare, beautiful, improbable things are exactly where they're meant to be. Good night. Thank you for drifting through these quiet possibilities with me, for letting your mind wander through worlds that never were, and for returning here to this world with new eyes and a deeper sense of wonder. If this journey brought you peace or curiosity or a moment of stillness in a too busy world, then it did what it was meant to do. The universe is full of stories, and we've only touched one tonight. There are more waiting stories about stars that never die, planets that shouldn't exist, and the strange, beautiful accidents that make life possible. So, stay a while if you'd like. There are more quiet nights ahead, more questions to drift through, more wonders to explore together. Until then, look up, notice the moon, and remember, the light falling through your window is older than anything you'll ever touch and rarer than you ever imagined. Sweet dreams, and see you in the next story.